Okay, so I think we shall start. It's my great pleasure to have Chuang here. He's interviewed for a position in my group, and he comes with a rich computer vision background. His advisor is Andrew Yao. I don't know how you could pick up a research topic which is totally out of your advisor's domain expertise. But Chuang has a very rich experience. He did visiting research student role in Stanford, CMU, and also did a bunch of internship in both Microsoft Research Asia and Google Research. So, Chuang, the floor is yours now.
Okay.
Look forward to it.
Okay. Thanks for Gang's introduction. And okay, today it's my great honor to be here to present my PhD work, Video Understanding from Text to Language. And currently, we are in an era of big multimedia data. In a single minute, there are about 300 videos will be uploaded to YouTube. Then, a natural question will arise. How can we organize this large amount of consumer videos? Okay, let's first take a look how YouTube could achieve this goal. YouTube conducts video search based on the keyword match between user queries and the video metadata, such as title, description, or comments. Yes, this is actually a very effective way and efficient way to conduct the video search, but there also exists some problem for the video metadata. The first one is the video metadata could be null or irrelevant, since when a user uploads a video to the website, we cannot expect them to give a perfect title that exactly matches the user searching behaviors. And secondly, we also observe there are large or quantity videos that don't have the video metadata at all. So both of these cases, video search will be fail. And it will be a pressing need to conduct content-based video analysis. And my research focuses on understanding human actions and high-level events from web and consumer videos. Particularly, in this talk, I will first introduce my effort at designing effective network architecture to learn robust video feature implementation. My paper published on CPR 2015 is one of the pioneering work that deep neural work achieves success on the video recognition task. And we also provide the best model on track with multimedia event detection competition and also this year ActivityNet challenges. We also provide a single best model on the YouTube 8 million challenges. Even though supervised deep neural work achieve reasonable good performance for the video recognition, but we cannot expect this kind of supervised learning can scale up. So in the second part, I will introduce our effort at learning video recognition from mixed supervision. First, I will show how web cloud web images and video can replace the human annotating example to conduct video recognition. And secondly, I will show that how we propose a new method to conduct zero-shot video recognition by connecting with knowledge base. At the end of my talk, I will introduce our most recent effort that connect video understanding with language through attractive visual captioning and visual question segmentation. Okay, let's first start from the video recognition part. Currently, there are three challenges for the video recognition. The first is that video data has large inter-class variation, and also its inherently very complex, make video recognition become a super challenging research topic. And secondly, it's very expensive and also time-consuming to annotate the video. This is also the reason why current video recognition datasets are all concentrated to hundreds of classes, much smaller than the image data. Thirdly, we also observe that there are a wide range of video concepts, since a video concept is always consists of action, scene, object, so the combination is very complex with the video vocabulary super large. To address the first challenges, we propose that we learning video representation using deep neural work. Okay, the problem we want to solve is that given a video for testing, we not only want to give a video level event label, such as this video with name is as a tapping back trick, and we also want to localize the spatial-temporal key evidence. For example, it's a search snippet containing the back jump, and also it's a back view, making us it's a back view instead of a background window, make us believe it's a tapping back trick. And to achieve this goal, we propose an untrainable deep event network. And our deep event network actually is inspired by the RCN-based framework. And we first pre-train the network using the image data, and then we fine-tuning on the video data side. However, different from the existing approach that that they treat video classification as the image classification, which I mean that he takes the keyframe in and feeds forward the network. And finally, they aggregate the softmax score over all the keyframes to achieve final video recognition. And we think that video is natural, has a temporal dimension, and we should cleverly leverage the information contained in the video to achieve the video classification. So the first technical contribution that we propose, we switch from a single image to multiple keyframe, or we call it as a video segment. That we put the video segment as input of the network. And the second contribution that we propose, a learnable feature aggregation layer here is we name it cross-free map pooling. That's to learn how to aggregate the feature annotation from multiple keyframe to a single vector and then put it into classifier for backpropagation. Equipped with these two technical contributions, we achieve the best result on the track with multimedia event detection data side. I want to mention that we boost the previous step by relative 40%. And the traditional approach of input and trajectory feature vector, it dominated video recognition for several years. And our paper is one of the first success on the deep neural world that beats the shadow representation. Since this is also a pioneering work, and we also want to understanding why deep neural work can achieve so good result. So we visualize the spatial-temporal saliency map of the to understanding what actually the deep neural work learn to localize during the training. We find that it definitely localize some very interesting, we definitely have some very interesting observation. For example, for the attempting back trick, the region with the people right back has high response region, and also for the dog show, the dog region also have higher saliency score. Another very interesting observation is about the false event. For example, the playing fetch. Actually, from my understanding, I don't know is the person more important or the dog more important than to distinguish the playing fetch. And also, I apply an off-shell saliency detection approach in the right mode. It told me that the person is more important. It's more saliency. But when I put them into classifier, he told me that it's dog more discriminate to discriminate the playing fetch. So there somehow indicate that the machine understanding the visual system is somehow not correlated with our human cognition system. Even though this paper published 2 years ago, it's already received quite nice attention. For example, I want to mention 2 works about the video network architecture design. And the first work is the winner of last year ActivityNet challenging, the main temporal segment network. And in that technical report, sorry, okay.
So before we move on to the next
Sure.
one, the last one, did you just feed it the whole video, or you somehow get some shot from the video first before you feed it?
Yeah, that's a really nice question. We definitely first decompose the video with the different segment, and we only extract the middle keyframe as the input of network to save the computation type.
How do you decouple?
Yeah.
Some
Actually, we based on the color histogram change, and means we can detect the short boundary, and then we define the video segment and pick the middle keyframe here.
So if the decouple is very bad, does it affect the final result of the keyframe?
Yeah. There's many paper talk about that how can we clearly do the video segment, and from our observation, it definitely will improve some later, but not as much as we expected. Yeah.
I see.
Are you using any motion information or only static cues?
In this paper, we do not use motion information, and but in the next slide, I will introduce something about how we leverage different temporal information. Motion information, and even so, let me continue my talk first. And actually, this paper published 2 years, and I want to mention 2 works. The first one is the temporal segment work. It's the winner of last year ActivityNet video classification challenging. Actually, in this technical report, they clearly indicate that their success borrowed my first technical contribution, that he using the video segment instead of keyframe as input to improve the traditional two-stream network. And what they do one step further, that they also apply this method to optical flow input. I mean, it's just a question about using the motion information. And the second one I want to mention is the winner of 2015 two-mode challenges. Actually, they have the same idea of my second technical contribution. That instead of directly average the soundbite clarification, they're also using feature encoding. But instead of using our method pooling, they use more advanced VLID encoding to do the feature aggregation. And also our work has received attention on the video localization and also network interpolability. And I think you're more interesting about the recent progress. And this year we win the ActivityNet challenges. So I'm not sure how many people know the ActivityNet. Okay, ActivityNet actually I think it's more like email classification in the video domain, and many competition, many people take part in. Also, I think this year Microsoft also take part, Azure also take part in the competition. And here I want to share you something that why we can win these challenges. Some technical contribution. The first one I want to show you is about we propose super deep LTM. It's about 7 layers. Because original observation is that the deep LTM for video recognition is not useful, and we come with conclusion from some small data sets such as UCL1 HMD. I mean, it's only 10,000 videos here, and we speculate the conclusion that for deeper LTM won't have maybe from 2 reasons. The first one, maybe the data set is not enough, that we do not need such big model to capture the data. Second, maybe that we not clever designing the network architecture to make it deep. So to figure out what entails the deeper LTM network for video recognition, we first test on the YouTube 80 million data, because the emergence of YouTube 80 million and also the large scale ActivityNet, because they have multiple, they have significantly bigger set of video that they provide our opportunity to revisit our conclusion. But when we naive increase the depth of the LTM, it still entails bad performance. And then we found that because we speculate the reason that for the deep LTM, they have many recurring units and make the backpropagation and gradient extent not work well. So here we propose that we add a we add a fast-forward connection between 2 recurring units. And with this short cloud, we find that the model can work fast and also better and entail better performance than the shadow network. And the second one I want to share is about we propose a purely attention network, because we are inspired by the recent success from the Google Brain. They say that purely using attention network, it can achieve really good performance on the machine translation. And we tried the same, very similar idea on the video temporal modeling. And we definitely observed that only using attention without using LTM, it also achieves really good performance. And different from them, we propose in a shifting attention layer is inspired by the spatial norm, that we introduce some learnable parameter here, and we learn about 64 attention layer and the learning parameter involves that to learn diverse attention here, and then we combine them for better video recognition. And the third model we propose is about using the temporal convolution network to replace the LTM and other recurring units. And the idea here is that we found that it's also inspired by the recent success on Facebook, that they propose using conv sequence to replace the LTM. They also achieve really good. And we have the similar observation that if you simply using the temporal CNN to go through to go across the frame, is really good and compared with LTM RNN framework. And last one I want to show you is that we also revisit the backpropagation method when we training the network for video recognition. The intuition here is that we find that for video recognition, we do not using all the video segments for the video classification. We only need to focus on a small side, a small and diverse side. So here we propose that during the backpropagation, we do not backpropagate all the keyframe or video segment. We only select some most discriminative and also some there are some diversity constraint to backpropagate a small part of the video segment to do the fine tuning. And we found that it will entail better conversion rate and also better performance. here I introduce that's about how we design the network architecture for the supervised video recognition. But as I start at the beginning, that we cannot expect this kind of method can scale up at the video recognition. So in the second part, we introduce how can we learn a video recognition model from weak supervision. The intuition here is that when I put a query on Google image search engine or Google YouTube video search engine, that we find the top return images and video are always quite relevant to the search query. So my speculation that can we using this web cloud images and the video to replace the human notice examiner to train a deep network for the video recognition. If we can achieve this, it would be very cool to scale up the video recognition. We can train whatever concept we want. Even though this is really good thinking, but it's super challenging because both web images and video contain certain nodes. For the web video, it suffers problem of the unfocus. I mean that you can see the first sample, the mapping flow. Most of the video frames is not about the mapping flow. Only a small part in the middle belongs to the mapping flow. So video have the problem of the untrim that only a small part of the frame are relevant to the action or event. And the web images has the benefit that because it's always web capture and it also contains the highlight of action. But it may suffer from problem of some domain gap and also the semantic drift. For the semantic drift, you can observe the second example for the juggling ball. The return web image about the ball, not about the juggling ball. So we cannot expect such of images can work well on the video domain. And for the third image, and for the third row, we find that the baby crow web image, they are definitely the baby crow, but they are all in the white background. We cannot, it's a has distinct domain gap with the video cluster background baby crow. So we cannot expect that such clean web image can work well on the video domain. So it seems very difficult to remove the nodes that simply be using the web image or video frame because it's more like supervised learning. We do not have any guidance here. But we have a key observation here that we find that even though we cannot remove the nodes from web images and the web video, but if we can jointly consider, we have some chance. So the observation here is that we find the relevant web images and the video frame are typically very visually similar, but their irrelevant part has their own distinctives. For example, for the nodes from the web images, there are all some logo or some logo images. It's not always occur in the video frame, and the noise part of video frame is always some background for them audience something. It always not occur in the video. In the web image noise part. So it seems that the problem can be solved that we can do the mutual filtering that keep the visual similar part, keep the visual similar part in common together, and then both of the nodes will be removed. Based on this observation, we propose a lead EC network, and we first take the video keyframe as the input of network, and we train a leading network. And this network do not have the ability that to distinguish, the relevant video frame or irrelevant part. But it has one benefit that it can be used to distinguish the relevant web images. Because I told you that the noise part the noise part from web video and the web frame are very differently. So the visual similar web image are always a highlight and also relevant to the query will be ranked higher. So we can apply the leading network to the web images and get some probability score, and we can based on the probability score to set some threshold, and then we select the highly related web images. And since the web images always contain the highlight, so it can be put into the network to train an existing network. And then the existing network will have the benefit to localize the action, and it then can be back to trim the video frame. So during this iteration, both of the nodes of the web images and the video frame are removed. So we can then train a temporal model to model the temporal information. Here we show some ability study comparison result. First, the result of when we first train on images, or we purely train on all the video frame, we will get around 60% accuracy. And if we if we train on LeadEC, it will improve almost it's over 10%. It means that John utilized them is very useful for video recognition. And we also compare with results for other alternatives. For example, we train two models and we using late fusion to in some of the two model. It's also better by single using this model. And also we try the method we mix all the web image and video together and train one network. And it also has some benefit, but it's still, the performance is still behind our LeadEC way. That we first train on web video frame and then we using the video the web image to exceed it.
Do you use the same network for
Exactly, yeah.
video?
Yes.
But videos typically will have MPEG artifacts which images don't have. So did you try changing, let's say, the early filters, which are more specific to each modality rather than just mixing them up?
Yeah, this is why I separate the result of the noise mixing and also the mixing. The noise mixing is that we just plan them. And the mixing is that we also apply our filtering method, and then we mix all the images to retrain a network. And you can think that our LeadEC way also entail better result.
And then
okay.
the problem which you mentioned that web queries, for images and videos have a lot of label noise, right?
Yeah.
So it's not clear to me how you're addressing that problem when you use images.
Okay, this is what I described using the LeadEC network. I can give a general understanding here. So the intuition is that the noise of web images and video the irrelevant part are differently, but their relevant part are also similarly. So this means that you train a network that you see some similar example, they will have higher detection score, right?
Okay.
And then the relevant web image will be selected. Yeah, the web images with very similar appearance of the video frame will be ranked higher, and it's not very similar part will rank lower. Then we can set the threshold to remove out the noise web images. And then the relevant web image will be highlighted. Web images has the benefit that they are always highlight, right? So you can put them into the network to further fine-tuning it. So it see more highlight of image. So it can so the network will have the benefit to distinguish the highlight. Then it can be back to test on the video to select the top ranked video highlight.
One. So when you test the web crawl data to find related data, do you use some attention or you test the entire image?
Here we do not. So this is the next question. And in our previous, when we publish the paper, we do not using attention. We just using the detection score as a kind of attention. But we definitely find some follow-up work. I think published on this multimedia, they revisit this framework is some attention method. Yeah, I think there are many different methods to do here, but the intuition here is that how can we remove now? Okay.
And also you can see some positive data mining. Did you try to repeat this bootstrapping, I guess, to retrain, collect the data and retrain? Did you find any benefit to repeat this process more than one time of mining positive data?
Yeah, so the question of him is that because in my paper I'm only do one iteration, his question is we multiple iteration, how to prevent. Yes, actually this question also asked by some the reviewer also asked me this question. And we definitely found that during multiple iteration it have maybe 0.2 some improvement, but it's not such big thing. I think it's also have some covered curve during multiple. Yeah.
True.
Also, there could be a tremendous data set bias, right, between the images and videos which you are using for doing the weak supervision. So have you tried training on one kind of data set and trying it on a completely different data set to see if there's generalization?
Yeah, that's next question. And this is actually what the results I want to tell you here.
Okay.
So it's we also test on the trackability multimedia event detection data set that we crowd the video from web that we do not use any positive data because it's more like mimic. It's only the same query, but that there have some domain gap because the testing video get in second way. And we also compare with the performance with other methods. We also found that it definitely much improved the result using the LeadEC network. I think for the time constraint, I have to switch to the another part, and we can talk more about this part offline here. Okay, even though the web-based supervised approach can achieve reasonable good performance on the video recognition, but we cannot expect that we can train the deep neural on the web data we can pre-train all the video concepts beforehand. So this is where I want to address the problem. How can we achieve some zero-shot video retrieval? Is that how can we learn new video concept example without any positive data? Like how can we adapt the classifier? And the problem setting is that you gave a text query here, and also you gave a video. And for example, there are a text query, and maybe there are 20 or 200,000 video. How can we return a ranking list that how can you return a ranking list to indicate how the video is relevant to the query? So it's more like a traditional text-based video retrieval approach. And the traditional approach, so the problem is that he embeds the video and the text query into a common feature space, and then they will rely on dot product to achieve retrieval. I agree this is a very effective and efficient way to, the retrieval-based approach to achieve the goal. But regardless, this is not optimal because it cannot leverage the inter-class relationship contained in the new video concept category and the predefined, some known video concept category. And to address this problem, the intuition of work that, for example, if I want to recognize a new video concept category for one with the soccer penalty, even though we do not have this kind of positive data, but we may have some we may have some training data of field hockey penalty, soccer juggle typing that. Our observation is here is that if a video very similar to both field hockey penalty and the soccer juggle, it will be very likely to be the soccer penalty. In other words, if a video have both higher detection score of field hockey penalty and the soccer juggle, it will be very likely to be the soccer penalty. Then the problem turns to, given a new video concept vocabulary, how can we identify the relevant concept from a large predefined concept pool? And to address this problem, we're using a data-driven word-to-vec approach is that we compute the semantic similarity between two concept names. And let's give a concrete example. For example, if there's a novel video concept category such as front crawl swimming, and there are also a lot of predefined concept pool, and we will compute semantic similarity between the front crawl swimming with many predefined concepts, and then we will have a ranking score of all the video concept name, and then we will, for example, for the front, we will find that the higher relevant concept will be black crawl swimming and baby crawl. And then we will training a ranking function that makes the video very similar to the baby crawl and black crawl to rank higher, and as some videos similar to volleyball swing, something are ranked lower, so we will recognize the new video concept. And by leveraging this technique, we achieve the best result on the track video multimedia event detect combination. And the only secret that we beat with other teams so much is that we cleverly leveraging the interclass relationship between the concept instead of other team always trying hard to improve the video embedding or word embedding, how to measure their correlation. So we address the problem in a quite a different way. Okay, let's go to, I want to introduce some more interesting thing. I think about vision and language. The first one I want to introduce about the visual captioning part. Is about how about generating attractive caption. Okay, the problem we want to solve is that you gave, I'll argue upon that because many people doing image captioning and many people will argue what's the real application for the visual captioning. And we also found that the current state-of-the-art visual captioning system always generating a global description of the image content. That the captioning side is very boring. And we argue that instead of sending image that the people use smartphone, a smart girl sit on the beach, we can say it in a more attractive way. So, for example, smartphone, you not make me smarter. Pretty girl, don't love me. So in such kind of visual captioning is more attractive to me. And also we find that attractive captioning also have some another benefit is that you can see these images. The images become popular not only because the image content, it's also because they have a perfect title. So, and also another application I want to mention is that, for example, is when I upload the images to a social media such as Facebook or Flickr, it will always take me a long time to figure out an attractive caption or title to describe images to attract more people to like my picture. So if machine can automatically generating some attractive caption, it will be very, very useful. So, and we also found that using style is a kind of method to make image caption attractive. And in this work, we study how can we generating romantic style and humor style captioning. And the methodology of our approach is that we propose a factor at a time. And actually, the factor I think very easy is that we decompose the weight vector of original. We decompose the matrix of W of the original item into 3 parts. USV. I want to first mention USV is not equal to the SVD. It's just 3 learnable parameters here. And so what we want to do is that during the caption generation, we want to separate the content part and also the language style part. So we hope U and V to control the content of the, during caption generation, we want using the U and V to control the content of images, using L to do the style specific. And to achieve this goal, we leverage 3 kinds of data. The first kind of data is the paired images and the factual caption. It's the paired data of the traditional captioning. And then we also have the monolingual romantic sentence and humor sentence language corpus. Since that it's very hard to gather the romantic or humor, the paired images with romantic sentence and humor sentence. So we want to achieve the goal in an unsupervised way. So during the first, we want to U and V way to capture the general comment. So during the multitask training, the first part is that you condition on images using the factor LTM to generating a caption. It's more like the traditional encoder-decoder baseline. And for the second task is we using the factor LTM to do the language modeling. Is that you give the first word to predict the second word, as so on. And also the third task is also condition on the humor sentence to model the language pattern on the humor sentence. And during the multitask training, we share the weight of U and V among different tasks. And S is style specified. Then it will enforce that U and V to control the content, to capture the common thing in the image caption generation, and S to control the style. And during the caption generation, we can just switch the style vector of S to generating the desired caption we want. For example, if we want to generating the standard style, we can use SF. If we want to generate the romantic sentence, we can use SR. And if we want to generate the humor sentence, we can use SH. And let's see some concrete example. And this is the caption generating by the caption bot. It's about a dog laying in the grass. And our romantic sentence will be a dog running through the grass to meet his lover. And also the humor one will be a dog running through the grass in search of the missing boys. And let's give another example. For example, the caption bot will say some boring sentence that a man on a rolling hillside next to a stone wall. So it's really boring. And we romantic, we can say a man is climbing to conquer the high. And also the humor one will be a man is climbing the road like a lizard. And we also show that our method and data can also be transferred well to the video domain. For example, for this video, the standard style caption may be a man is playing a guitar. And the romantic caption will be a man plays the guitar, dream of being a rocking star. And the humor caption will be a man is playing the guitar, but runs away. So in such of caption is more attractive and also makes the image in video caption also more popular.
But the only way you can generate these is if in the training data you have some forms of these, right?
Yeah, this is that's a really good question.
You're not being creative. Your network is not being creative here. Really, it's copying things, right?
So first I want to say, it definitely like during training, it definitely such as dreaming up with some kind of language pattern contained in the language corpus. But I don't agree part is that it's just copy the sentence from, because we definitely find that the factor LLTM just learning, for example, for some dog people always using such of, for example, find the missing ball to model such of pattern. And it's more like modeling modeling the concept and how people always make this concept being romantic or humorous.
So what would be interesting to see is these generated sentences, if you go back to your training data and have some semantic distance between your input captions, what were the closest ones in the training data? Then only it makes sense to understand what you're doing here.
Yeah, it's a really nice question. And first I want to tell you is that because we do not have pair images of romantic sentence, so this means that you cannot use any nearest neighbor approach to achieve this goal because you don't have the pair images. So, and we also definitely find that for some language pattern that is occur very frequently in the language corpus, and it will generate. That the pattern will be repeated. Because our goal is that we want to instill that how people, when we come with some concept, how they make them into romantic humor. So actually, we also want to machine learning to be humorous and romantic. That when we call it sometimes. Yeah.
Yeah. So are these two styling data sets, are they separate data sets that you have labeled? Like romantic is from some book, or?
It's a really nice question, and it's also a really nice question. And actually, we train both. That we first test something like the romantic books, and also there's offshore from natural language processing people. They have some humor sentence corpus, romantic sentence. So we train on this. And during testing, it means that we label the testing data because we want to do the both qualitative and quantitative evaluation. So we do some evaluation for the human evaluation. Yeah.
So just practical comment here. It's very difficult to be funny when you want to.
Yeah.
It's much easier to be funny when you like your romantic sentences are all funnier.
Yeah, I agree. This is more like a
So you shouldn't really be doing anything with humorous data set. You should just be, and you shouldn't even do the romantic data set. You should do like Donald Trump. You should do things that are much more personal style. Person style that really stand out.
Yeah, actually, we do not want to differentiate different style in our paper because as you tell, you can see our title is about attractive caption. That we do not distinguish is romantic or humor style, but what we want to do is if we can generate more interesting caption. So during the evaluation, we also do a very interesting human evaluation here. That we generating, we give an image here, and we random shuttle about our caption generating from other system and our system, and we ask the user one question. If you want to upload these images to the website, which caption do you prefer? So this somehow to reflect that.
And one thing we've done which is related to this is to just for question answering systems to make the answer sound like it comes from a certain style.
Yeah.
And one thing you can do is remove movie scripts like we did the Star Wars, and then it's pretty hilarious what comes out. You can give all these possibilities. It'll be a kind of cool tool for social media.
Exactly, yeah, agree.
Yeah, that actually brings up my question, but I want to readdress like Humphrey's question about the sentence copying factor. I think the older generation of the image caption is more like a retrieval-based approach, exactly doing what you were suggesting. But with LSTM, you have the chance to combine fragments of sentences from one sentence and the other from other sentences.
Yeah.
But my question about really this kind of style, I feel is much better perhaps to position this problem in the conversation, maybe in the dialogue. Because really you need to take into other factors into consideration, like what's the question, like what the other person's personality.
Yeah, maybe some conditionals or something. Conditional information.
There is be some other factors, like even considering social network is actually loosely connected, like a dialogue, right? Like because you are making comments, some people will respond maybe 2 days later, not immediately. But in the chatbot scenario, you need to sort of take those contexts sort of immediately, I think. So this piece of work is in collaboration with Xiaodong.
Yeah, this is my last summer internship project.
It's our MSR project.
Yeah.
My other question is, in your USV decomposition,
yes,
it's infinitely ambiguous, right? I can multiply by any affine transformations, inverses, and nothing will change. So,
Yeah.
so how do you
Okay.
regularize it?
Yeah, this is a really nice question. And also ask, I will ask this question multiple times when I present this work. Yeah, and other people, okay, let me come back to the slides. I think we have enough time. Yeah, maybe we can come from the factor item here. Many people may ask that why do you decompose the W to 3 metric? Why do you decompose just 2 metric? Yeah, I mean, say you can using U and S with V and U control the content as control style or vice versa. And we definitely when we start, we definitely train. We train 2 factor, and we find the performance of we factorize into 3 part is from the performance is more robust to 2 metric. And we speculate because you and me, you come to constraints from mathematics, it will have larger search space and it will entail robust results. And the intuition why we controlling the style using the metric factor region. The first one is because it's very simple, and also is well utilized in the style and content. I mean the style and content control. I mean in the commemoration, for example, there are static background and also there are person way work. There are some methods that using metric factorization that can separate the content and the motion part. And we borrow the idea and we also work. We make it work on the LTM for the captioning generation. I think this is the whole story. Okay, I think I have to. Okay, sure.
So if S, you conjecture that S is encoding style in this factorization, and you can test that, right? So you can put in an input and then actually change the values of S by hand and see when you get a different.
Yeah, this is really this is really nice question. Is actually this is our the intention of journal work we want to do. Example, we want to do some mixed style. For example, 0.5 romantic, 0.5 humorous. I want to say in this kind of framework because you need it's more like there's no controller here that for this kind of method it cannot work. But we have another version is that we using Y, we multiply something that we definitely can do some mixed style and also really cool result. But I don't cover this in this stuff because it's under submission here.
But for that part, I think I agree with the approach that perhaps doing 2-person mixing 2-person style becomes more interesting than just sort of. Yeah,
I agree. Yeah, it's more cool to do some. Like it's also to reflect how we can control the style. How much style we want to, it's more like the controlling method for that, Okay, so it's fine. I also want to give another example, and also they actually also work with Xiaodong, and because last summer we also talked about that for image captioning generation system, we want to more deeper understanding of the image content. For example, the traditional visual captioning system, for example, for this image, you will show that a herd of elephants stand next to a man. But with more entity recognition approach, for example, the researcher Lei Zhang, he has really good entity recognition. He can recognize, for example, this person is Obama. And we can say that a herd of elephants standing next to Obama. But we can do one step further. We can combine knowledge base to do some reasoning. For example, Obama is the president of the Democratic Party, and the competitor of the Democratic Party is the Republican Party, and the mascot of the Republican Party is the elephant. So we can come to a very deep understanding of image that Obama is chased by his Republican competitor. So this is I'm thinking of the next step of visual captioning. That because the first sentence is just maybe a 10 years boy, he will come out sort of caption. But if he grow up and he has more advanced intelligence, he will generating the more deep understanding of the image content. Okay, I think at the end I will introduce my most recent ICC paper that how can we best collaborate joint modeling, vision, and language through the new task of visual question segmentation. And the problem we want to solve is that, for example, we have an image and we have a question. I think most of you is very familiar with the traditional visual question answering system. That you give a question and you give a question about images, he will generating a textual answer about the images. And they will argue that the visual question answering is a very important step that to measure the machine intelligence to both understanding the image content and also the natural language part. So it's a very significant step for the jointly modeling of visual language. However, we argue that only providing the text answer is not enough to understanding the image content here. So we argue that instead of only giving the text answer, we should also provide the visual evidence or the visual segment how you answer this question. For example, if it's the second question about is the street empty, if you just answer yes or no, actually you have 50% to get the to get the right answer, right? But no one knows that you fully understanding the image. For example, you find there are two cars here, so so the answer is no. And also, is he wearing a tire? Means that you also do not know that if answer yes or no, that you don't know that machine definitely know where the tire is it. But if we can localize the tire, means provide another visual answer, it means that you definitely understanding the image content. And so we propose that, yeah.
So I always had a little bit trouble, on the visual question and answer problem in the current setting. Like it's all about you provide the database, you provide the question, then you ask the system to generate the answer.
Yeah.
Is it even more important to be able to see the picture? That
This is our
question.
Yeah.
This question setting is. So a little bit off, for example.
For example, what's the sports is always about playing tennis. If you just understand this playing tennis, you will be 90% will be correct. And for some, I think Don asked the question is also another argument of why we want to do the visual evidence is that if we only train on language and answer pair, you will get a reasonable good performance. Not big improvement when you look at the images. So this is the reason why more people for visual question answering it should different from the question answer. We should put more priority of the images. So I think there are in concurrent with this work, there are another work from the original VQA tool is that they will they try very hard. To control to give a question to generate more diverse answer. But we saw it in a different way that instead you also localize the visual evidence. I think it's another very easy way that to evaluate, to highlight the importance of image content analysis for the VQA task. And with this data set, actually we show that it can be benefit to two fundamental tasks. The first task we show that we can enable a new task about the question focused segmentation. That you give a question that you tell me that which region can answer this question. And also computer vision task can also be cast. The question semantic question segmentation. The question focused segmentation can include many computer vision tasks. To unify all the computer vision tasks in one task. For example, what the object is, what is it? Something question like this is more like the object detection problem in computer vision. And how many question is more like the semantic segmentation or instant segmentation. And also for some, what is the man doing is the action recognition in static images. And so also some action localization question. Also something about reasoning. For example, there are question about is he married? If this man married, if he can localize the ring, that means he's married. Also, is there any commercial shopping? Then maybe localize some McDonald's, something like that. So this is the first task. Second, we also show that with this segmentation mask, we can do supervised attention for VQA. Is that during the trip, because the pupil currently attention method is more like a black box that you give the question and machine will automatically attend different region. And also there are many papers that show that even the attention is not very reliable. And here we show that if we can training on the with the question, region, annotation, and the answer pair, that we teach machine where to see when we train the VQA model, it will also significantly improve the performance. Here I want to show you some results. First of all, I want to show is about the result of question focused segmentation. At the front table, I want to tell you that the best method we propose is still far away from the currently semantic segmentation result. This means that the pixel level image understanding from natural language is still very, very challenging task that we need more effort in this domain. And in the second part, we show that we only noted about 10% of the original VQA dataset with segmentation truth, and it will can improve the performance by 1.5. This means that if we can teach a machine to see clearly, it will do better for reasoning and also to answer the question or something. So I think it's a good start that for to teach a machine to see where to attend, and we can first understand the image content, then we do the QA task. Yeah.
When you analyze the query, do you the textual query, do you take in the entire question as a single entity, or do you break it up into like subqueries and do different image processing tasks based on what the subquery is?
Oh, that's a really nice question.
So
yes,
just
we
to
try
clarify before you answer, so if I ask like, where are the sheep in the picture versus where are the sheep and the cows in a single picture, would you break that up into two queries, or would the machine try and isolate that as a single query with two objects?
I think it's the second one. Is that we try both that we using some word twice for each word, and we average of them, and also we try that we tune LLTM that encoding the sentence into one single vector. I think currently we do not decompose the query for elegance, but I agree with you that if we can, there's this still open research problem. How can we deal? How can we understand the language? We separate them. I think it's still. And currently we only explore the second one is that we encode the.
Yeah, it's really interesting because the way that you attack this in as a database problem is you generate operators from text, and you sort of create almost like a query plan through the database. It'd be interesting to think of like an image processing plan that's sort of formulated the same way.
Yeah, I think it definitely many research we can do about the language part, and also many things we can do about image part. So that's why I say it's a really interesting task that I hope everyone can try this. Yeah. Okay, I think, okay, question.
So you mentioned that you can reason about the image, like is the street empty or how many single buses are there. Is it also possible to reason about spatial dimensions of the image? So for example, what is the animal on the left or things like that? Is that something that's part of this data set?
So I think your question is about the answer ambiguity, because for example, if, for example, you ask this question, for example, I think for example, for this one, what is next to the dog? And actually the question, so what indicated in the question is about the dog, and what the answer is the person. So definitely when we label this data set, we definitely found that then we have, there are many, hard to correlate it. So we define the rule that that we only like the user to annotate the answer part instead of what the question contains. For example, for this one, what's the next to dog? You only need to annotate the answer. This is kind of to avoid the confusion. And also during the labeling task, we also for some question, that means that you cannot find some reason as the particular reason for answer. And we also gave some answer another choice that means that you need to see all the images as answer, or you are unsure which one is. So we will delete such of uncertain, and we want the data set to be more clean, and and also we focus more on the pixel region based. We understand different region relationship and anti-relationship. So we lower down such of questions. So we deleted it during the data collaboration. Yeah. Okay, I think I should conclude my talk. And the first one I want to mention is my work is one of the first, so started using deep network for the large scale video classification. And also we pave a new research direction that how can we utilize the web, cloud, video, and image to do the video recognition. And also we propose a new method by connecting knowledge base to open vocabulary video retrieval. And fourthly, we take a step further to generating the attractive visual captioning. And finally, we collect a new visual question segmentation dataset to facilitate a better joint modeling and vision and language. And in the next step, I'm very interested to doing the following research topic. And the first one is about how using meta-learning to design the neural network architecture to do the video architecture search. Because you know that currently all the neural network architecture is human-invented. And we want to currently, actually, this program working in Google Brain is that how can we using another network to improve the network architecture design and to learning neural network, to learning neural network architecture by neural network. And I think it's because currently there means that in the Google Cloud or Microsoft Azure, that many people want to do some deep learning, that you only need to give data in, they will generate a good architecture. I think it will be very cool. Secondly, I also want to do more work about connect video understanding with knowledge base, as Obama list that because currently video understanding is still limited to the video level, and we should deep understanding what's content in the video content, what's the cultural relationship. And fourth, I will also want to understanding object like human training in video and connect video understanding with robotic. As I mentioned with the work, I think it's about, for example, we watch the video, how can we stimulate the action performed in the video, like the robotic to simulate the action. And also very interesting about using the generative model for the video for frame synthesis, for the future prediction. And last, I also want to treat video as a knowledge base. And how can we leverage it in the temporal continuity, content video for learning visual knowledge, for unsupervised feature learning, for novel view synthesis. I think there is many work we can explore here. Okay, I think that this is all my talk. I'm very happy to hear, and thank you for my talk. Okay.
We're almost on time, but in case you have any questions,
yeah.
I think we can still allow 1 or 2 questions here.
So in Lead to Exceed, when you choose which images to let through for retraining, do you have a different parameter setting, different confidence?
Sorry, can you say again? You mean which work? You mean the...
In the Lead to Exceed work?
Sorry?
Lead to Exceed.
Maybe you can come to my... Yeah, sure. You mean the widely supervised approach?
Yeah, the web supervised approach?
No, we directly fine-tuning the network.
Yeah, when you do that,
I mean that we do not retrain the network, we just put the data in and to further fine-tune it.
Yeah.
Further update the network.
Right. You're fine-tuning it. So you're retraining some of the...
Yeah, we do not retrain, yeah, not retrain.
So when you do that, are you choosing the images with the same confidence?
Yes.
Because you reject some, so for every class you have the same confidence? Okay.
Yeah, we don't consider diversity in our case. And we just set one threshold to remove the noise here. Yeah.
So out of all the work which you presented,
yeah, it's all my first author paper.
which one do you think is closest to taking out of the lab into the real world?
Sorry, can you say again?
Which particular work would you say is ready to be
shipped to
taken
product?
out?
Yeah, I think that for the video recognition, for the learning, it's already in the Baidu video search engine. I mean that many algorithms is already transferred for the widely supervised approach. They already use it to train out video tagging system using my method, and also for the feature learning, and also they work on the video recommendation system. Yeah, many product transfer. Yeah. Okay. Thank you. So what may I know?